meet met Electron. It doesn't meet anymore, such a simple songs. Bohmian Rhapsody.
Everything changed after that. Thank you very much. Thanks for this wonderful opportunity to talk here. The two people in the picture is Marcel Rees on the right and Harish Chandra, a mathematician. They're both mathematicians on the left, and you will see why I have their pictures up in this. I'm going to start by a sort of kind of a prophetic quote from Einstein. The manifestation of light's electromagnetic waves is constrained at singularity points, like the manifestation of electrostatic fields in the theory of the electron. In such a theory, the entire energy of the electromagnetic field could be viewed as localized in these singularities, just like the old theory of action at a distance. This is from 1909, a paper about on the development of our views about the nature and makeup of radiation. Einstein thought about the problem of light, what light is, for a very long time, before his entire career. And this is another quote, but what is light really? Is it a wave or a shower of photons? It seems as though we must use sometimes the one theory and sometimes the other, while at times we may use either. We have two contradictory pictures of reality. Neither of them fully explains the phenomenon of light, but together they do. This is from 1938, the book with Infeld. And finally, near the end, 50 years of thought have not brought me closer to the question of what light particles are. Today, every simpleton thinks he knows the answer, but he is fooling himself. This is from a letter to Besso in 1951, and thanks to Avi for pointing out this last quote. So indeed, I'm going to be talking about our, just in time, the work that Michael and I have done about this question of if photon is a quantum mechanical particle, what properties it would have to have. What would be the wave equation and the wave function of the photon. So first, the first step in building such a theory would be to find what is the wave function and the relativistic wave equation for this particle. So it is clear that if photon had a wave equation, it would have to be derivable from a relativistically scalar and massless Lagrangian. Why? Because we do presumably expect to have conservation laws, conservation of energy and momentum and angular momentum, and such things under Noether theorem would have to come from a Lagrangian formulation. And the massless, because photons are massless. Similarly, this wave function should evolve as a spin 1 wave function with no longitudinal modes, yet with both helicities. This is because this is what we understand how a photon is, how it behaves. It has to obey the Einstein dispersion relations, which
Maybe you want to explain to some people what longitudinal modes.
I will come to that later. Yes, so it's just listing the properties that it would have, and this I will go over these things again. And it needs to yield a self-adjoint Hamiltonian and a probability density for the photon location obeying Born's rule. So, and if all of this sounds like a tall order, it's important to realize that for the electron, the corresponding things have been known for a very long time. So, indeed, in 1928, Dirac wrote down the relativistic wave equation for the electron, which is a spin-half massive particle, and he showed that this would have to have 4 components, this wave function, and it would satisfy this equation in which the matrices that are involved are 4x4 matrices providing a representation for a certain Clifford algebra. So now, it didn't take very long before Oppenheimer could come up with a similar thing for a photon. So he wrote down this equation in which now the wave function had 6 components, but it had to be viewed as embedded in 8-dimensional complex space, and it would be, the operator would involve 8x8 matrices, which would give a representation of a different algebra. Oppenheimer himself was the first person to note that this equation he himself had written down had many, many problems. And this paper is really extraordinary. I haven't seen anything like this. He uses 10 pages, the first 10 pages. He lays out this beautiful theory of what this equation needs to be, and then uses the next 10 pages to destroy this thing with all his might. So that's, which in the end, you get a feeling that he really totally regretted ever having written this paper, which is a very strange thing. So you don't see that very often. And in 1939, Kemmer was able to write down a massive spin-1 wave equation for mesons, which at the time were thought to be elementary particles. And as you can see, now the wave function has 10 components, and the matrices are 10 by 10. So apart from the worrying fact that this number of components keeps going up, and you wonder at what point this will be too many, it seems now that if we do have a wave function for a spin-1 massive particle, it should not be very difficult to get a wave function for a spin-1 massless particle. Just set the mass equal to 0. What's the problem? So it doesn't work. And you try to set mass equal to 0, this equation has only trivial solutions. It gets there are no non-trivial solutions to this equation when you put the mass equal to 0. So that's not the answer. So this brings us to the year 1946, where two papers were written, two physics papers by two mathematicians. Both of them were ignored completely by the physics community. And Harish Chandra was an upstart young physicist at the time. He has just gotten his PhD under Dirac at Cambridge, and he, shortly after writing this paper, accompanied Dirac, came to the States and went to the institute, at which place he had a conversion and he became a mathematician and never worked on physics again. But before doing that, he did write this paper where he realized that you could get Kemmer's equation to model photons if you replace the mass term with the projection term. So you take those 10 component wave function and you zero out the last 4 components, and that equation has all the properties, well, most of the properties that photons should have. There were still some problems with it though. For example, he had to assume a reality condition, and the reality condition somehow meant that the underlying Hilbert space could not be a complex over a complex field, and that has problems for a quantum mechanical perspective. He also was not able to produce any non-trivial probability density. So he wrote something which was some current that was conserved, but when you took the reality condition into account, this was always 0. So it didn't give him anything to work with. So he left it there. In the same year, Marcel Ries, who was at that point, a senior mathematician with many years of experience in analysis behind him, Fourier analysis. And he was very interested in physics, and in particular in quantum physics, and he wanted to make this precise, put it on mathematical, firm ground. So he realized that Dirac's electron wave function, this object that has 4 components, actually belonged to the minimal left ideal of the Clifford algebra. And he proposed that to understand this equation better, first we have to extend it to the whole algebra and study it there, find all of its conservation laws, and then descend to the minimal left ideal afterwards. So now his psi is itself a matrix. So now we are getting somewhere. This has 16 components now. Of course, he was very excited, and he talked to all the physicists in Lund where he was, and their reaction was basically, what the heck are you talking about? I mean, what is minimal left ideal? What is this nonsense? You don't need any of this. So he was completely ignored. So just at this stage, I can tell you that what Michael and I did is that we said, okay, what happens if you take the m in the equation that Ries has and replace that with that projection of Harish Chandra? So, and if you do that, you get our photon wave equation. So this is sort of just to give you in a few words. By the way, this is an interesting quote from Harishchandra. He did really have this conversion into mathematics when he came to Princeton, and he found out that not all functions are analytic. He decided he couldn't be a physicist anymore. And so, okay, we want to talk about electrons and photons as the abstract of the talk suggests. The conundrum that Michael and I have is that the abstract to our paper was written 87 years ago. And here it is. The Compton effect at its discovery was regarded as a simple collision of two bodies, and yet the detailed discussion at the present time involves the idea of annihilation of one photon and the simultaneous creation of one among infinity of other possible ones. We would like to be able to treat the effect as a two-body problem, with the scattered photon being regarded as the same individual as the incident in just the way we treat the collision of electrons. So this could very well be the abstract of our paper, except it was written in 1932 by the great physicist Darwin, and this is the person who actually solved Dirac's equation and found that it gives rise to the correct spectrum for the hydrogen. So luckily for us, Mr. Darwin did not succeed in carrying this through because he didn't know what to take as the wave function of the photon. So that's now this idea that what we are doing is not possible has a long history which I can't go into. But for example, we have this code. In fact, no satisfactory quantum theory of photons as particles has ever been given. This is by authors of the influential laser physics book, Sargent, Lamb, and Scully. The Lamb in the middle is the Lamb shift guy, the Nobel Prize winner. He wrote a paper called The Anti-Photon, in which he said that there is no such thing, it's just a convenient way of talking about stuff. And he seriously proposed that if you want to write a paper and talk about photons, you have to apply and get a license in order to do that. So fortunately, we didn't have to apply for a license. And here's another quote along the same impossibility line. The relativistic quantum theory of a fixed number of particles is an impossibility. And this is Weinberg, the quantum theory of fields, 1995.
That's not really a statement against the photon being a particle, just a particle number.
No, against this idea of electrons and photons. So because we are talking about a fixed number, then in what we are doing. So in that sense, it's against that idea. Okay, so indeed we can, inspired by Einstein's ideas and Bell's writings, we ultimately want to know what is the empirical electron, whether the empirical electromagnetism can be accurately formulated in terms of a relativistic n-body quantum theory of electrons, photons, and their antiparticles, formulated as a relativistic generalization of the theory of DeBroglie-Bohm, in which the quantum mechanical wave function guides the actual motions of these particles.
When you say n-body, you don't mean is that n has to be fixed?
N has to be fixed. Yes. N has to be fixed for us. Yes. It's quantum mechanical. So it's on the... in this theory, both electrons and photons are point particles guided by a quantum mechanical wave function. This is similar in spirit to Einstein's earlier speculations about the light quanta being guided by a ghost field. And at the same time, the DeBroglie-Bohm theory of electrons guided by their quantum mechanical wave function defined on the configuration space. So here's what we have done. Oh, by the way, this is a one-line description of the DeBroglie-Bohm guiding law. This is that you just need this one line, you don't need anything else. The wave function evolves according to Schrödinger's equation on the configuration space. Particles have actual positions, and their position is guided by this velocity field, which is the gradient of the phase of the wave function. And that's all. That's, so we want to do something similar. It is what I have written down is non-relativistic, what we want to do would be the relativistic version of this. So this is what we have done so far. We have formulated a relativistic quantum mechanical wave function and wave equation for a single photon in 1 plus d-dimensional Minkowski spacetime. It's a direct analog of Dirac's equation for the electron, and it furnishes a conserved quantum probability current that transforms correctly under Lorentz transformations. Together with Matthias Lienert, we have formulated and studied a fully covariant interacting two-body problem for an electron and a photon in 1 plus 1 dimensional Minkowski spacetime. We are making good progress towards extending the above interacting theory to 3 space dimensions and finding very interesting connections to the work of Cole-Fury on the standard model. If you remember, she gave a talk here about her version of the standard model. I will talk about the connection. We are presently using the 2-particle version of our photon theory, so 2 photons, to study phenomena related to entanglement. So I'm going to give you some more details about what is our wave function and what is the wave equation before I talk about the interacting system. So let me start with this Clifford algebra. So that's associated, every Minkowski space in these space dimensions has associated with it the space-time algebra. This is the Clifford algebra. And our photon wave function is an element of this algebra. Technically speaking, it's a section of this Clifford bundle over the Minkowski space-time. And with the so this is a matrix, imagine a matrix. And in 3 space dimensions, this will be a 4x4 matrix. It will look like this. So imagine it decomposed into 4 2x2 matrices. Right? And these 2x2 matrices turn out to be rank 2 spinors of 4 different kinds. So the fact that they are rank 2 means that they have 2 spinor indices. And there are 4 kinds of, their transformation rules depend on whether these indices have dots or don't have dots. So there are 4 kinds, all 4 kinds show up. And what's the question?
That was an ignorant question, so.
Okay. And the only the restriction that we have for this to be the wave function of the photon is that the trace of the 2 diagonal blocks is 0.
Maybe you should tell for us what Clifford algebras are.
So, sure. So you start with Minkowski space, or you can start with any vector space, right? And you want to define what does it mean when you multiply 2 vectors. Multiply 2 vectors and get a vector, right?
This is basically the exterior algebra?
It contains the exterior algebra. It's a bigger thing which contains the exterior algebra, right? So this is the same algebra of the Dirac gamma matrices. So that's the easiest way to connect it with what people know already. Yeah. So it's this particular multiplication, right, gives rise to this structure. And the signature of the quadratic form turns out to be important. So in this case, so every Minkowski space gets associated with a certain Clifford algebra, and then you complexify that to get this thing. So that's, but if you want to think about something in this algebra that you already know, just think of the Dirac operator. The 3 plus 1 dimensional Dirac operator is an element of this algebra, which is why it can act on the algebra. Because it's an algebra, it can act on itself. That's
operator without the differential symbols, no? I mean,
no, even with the differential symbols, it's an operator, but at every point it belongs to the cotangent bundle of that thing. So, okay, so there's the connection with work of Cole-Fury is that she showed that these 4 things, these 4 different kinds of spinors, arise in a certain canonical way from the generalized ideals of the Pauli algebra, which is the same as the complex quaternions. In fact, there are 2 more of these things corresponding to a spin half rank 1 spinners, and if you add those 2 to these 4, you get all possible representations of the Lorentz group. So that sort of allows us at some future point to view what we are doing as part of this larger scheme of things, which possibly could lead to the standard model. Okay, so here's our first theorem. The wave equation satisfied by this psi is a Dirac type equation, as I was just saying before, with modification inspired by Rees and Harishchandra. So as you can see, this is just like the Dirac equation, except instead of a mass term, it has a projection term. Right? One thing that Harishchandra does not talk about, yes.
Well, now, sorry to ask a very stupid question. It seems to me that the exterior algebra over a vector space of dimension k would
Right.
have dimension 2 to the k.
Yes.
Right? So this one is smaller.
Why is it the smaller?
Because you say the dimension is 2 to the g plus 1 over 2.
Right.
That's what you
Oh, I see. Yeah, that's what you mean.
said. So it's not larger,
Uh-huh.
as you said before, it's smaller, right?
Well, I guess maybe I misunderstood what is the exterior algebra.
The exterior
Yeah.
algebra is the sum of the exterior power, of all the exterior powers.
Mhm.
And so the kth exterior power of an n-dimensional space has dimension n choose k.
Right.
And the sum of it all k is 2 to the n. So that's the dimension of the exterior algebra.
But I was talking about there are matrices over that. Right? So what you're talking about is the actual algebra, and I was talking about what is the dimension of the representation. Does that make sense? So take Minkowski's 3 plus 1 dimensional Minkowski space, right? So that's 4, right? 2 to the 4 is 16.
Right.
This means you have 16 components.
Right.
But now you put these in a 4 by 4 matrix.
Ah,
That's the 4 that I'm talking about. Right. So you're right. You get 16, but then you see that that's a 4-dimensional representation because you get matrices, 4 by 4 matrices.
Blocks.
Right. The dimension of the
So,
representation
and
is
for
just,
dimension 4, it's a coincidence.
it's
that
a
the fours
coincidence
are the
that you
same.
just get 4.
If it was
Yes.
dimension 5, it would be
Yeah.
2 to the
So
4, it would be 16.
when the dimension is odd, there is a subtlety. So in 1 plus 1, so in 2 dimensions, this is just a 2 by 2 matrix. In 3 dimensions, this will be 2 by 2 matrices.
Mhm.
And then in 4 dimensions, it's a 4 by 4 matrix, and so on. So that's, it goes up. Okay, thanks for that. I hope that clears up. So, yeah, as I was saying, so Harishchandra wrote some similar equation, and I guess he betrayed his mathematical inclination because he did not put any constants in there. He did not put the h bar, he did not put the c, and crucially, he did not put this m-zap that we have put in there, which if we don't put it there, you will realize that this equation would not quite make sense because the dimensions don't match. Since we are differentiating the Dirac operator has differentiation in it, so you would think there has to be some conversion factor that, of the dimension of length or 1 over length or something. So that's what m-zap is there, but don't worry about it, this is not the mass of the photon. I will show that it is equivalent to a massless equation. So we just have this number there, which we have some conjectures about what it needs to be, but at this point it's just a dimensional conversion. Now, this equation is derivable from a Lorentz scalar Lagrangian. Just take my word for it. It is fully Lorentz covariant. That I guess we can see. And it still has some gauge invariance, meaning that you can add to the off-diagonal blocks any solution of massless Dirac equation. So, every component of this wave function satisfies the wave equation, satisfies the massless Klein-Gordon equation. So that tells you that this is really a massless equation, and it will give rise to the correct dispersion relation, right? A massless dispersion relation. The diagonal blocks of this satisfy the massless Dirac equation. The massless Dirac equation for rank 2 spinners, so if you take the Dirac equation and apply it to 2 by 2 matrices, it was known for a very long time that this is equivalent to Maxwell's equations. So this means that these diagonal blocks satisfies equations that are mathematically, I emphasize mathematically, equivalent to Maxwell's equations. And what that tells us is that there are no longitudinal modes. Now what does that mean? Solutions to Maxwell's equations propagate, wave solutions to Maxwell's equations propagate in some direction and they oscillate in the orthogonal directions to that only. There are no longitudinal modes in the sense that they are not like waves in water where there would be only longitudinal modes. Right? There is no,
like sound waves.
like sound waves,
Not like
right?
sound waves.
So that's, okay, so the spectrum, it is associated, there's a Hamiltonian associated with this, it is self-adjoint, and it gives rise to the correct Einstein relations. So everything is good, and here's the most important part. We have found that the massless Dirac equation has a conserved time-like probability current, so we can use that to talk about velocity of particles and so on. And this actually is based on a tensor that was discovered by Ries in that paper of 1946. After he generalizes the equation to the entire algebra, he proposes that he finds this tensor that is conserved, and then he says there are all these conservation laws associated to this, and we don't know at this point what these things mean. Well, now we know. So this is what comes out of the work of Ries, and here you can see what this is. You just form this quantity, you take your wave function, just take the diagonal blocks, the off-diagonal blocks, don't play a role in this, and form this phi bar, gamma mu, phi, gamma nu, x nu, where x is a constant vector field on the Minkowski space, and this vector field can be constructed from the initial data for the wave function. So it's not some extra thing that we put in there. It arises naturally. And if you form this quantity, you can see that it's a Lorentz vector, and it satisfies this equation that its divergence is 0. So now you have a conserved current. This current is time-like and future-directed, which means that its 0th component is non-negative. So you can think of that as the probability density, and the other 3 components will give you the velocity. So that's how we can move forward. So that was just for a photon. And now what we really wanted to do was interactions, because remember the abstract,
This X nu thing, could you go back?
Yeah.
You related it to the initial, but presumably it's got the same relation in it.
It is conserved, yes.
At any
That's
time.
right.
There's nothing
Yes.
special about the
Nothing
initial.
is special about, no, of course. Yeah. So it is, you can construct it out of the wave function, and then you realize that once you know it for the initial, you know it for, it's the same thing for all the other terms, because in fact all components are with a conserved quantities. So that's, okay, so now we want to do a two-body problem, say 1 electron and 1 photon. They are both relativistic, so we have to do a relativistic version of many-body quantum mechanics. So, which means, well, when you do this thing relativistically, right, the configuration space becomes the configuration space-time. So now, if you have 2 particles, you have to get 2 copies on the Minkowski space and take their Cartesian product, and that's your configuration space. So this space in 3 dimensions, this will be an 8-dimensional space. It has 6 space variables and 2 time variables. That's why it's called a multi-time wave function. So that's now we can put coordinates on it naturally, coming from the coordinates on the one-body Minkowski space, and we call them TESP for photon and TESE for time and space coordinates for the electron. And it turns out that the natural domain to consider for our evolution is the set of space-like configurations. So I will show you a picture of what space-like configuration means, but intuitively speaking, because we want to talk about initial value problem, it would make sense to think about configurations where there is a frame in which your two particles are simultaneous, sitting in one slice of time. And if the particle configuration is time-like, there would be no such possibility. So that sort of says that this is a natural domain. I will show you some pictures later. One can pose a Cauchy problem in this domain for the multi-time evolution of the two-body wave function by specifying initial values on this thing which we call the initial surface, where both times are set equal to 0. So this set of configuration, space-like configurations, has a boundary in the larger configuration of space. The boundary consists of light-like configurations, right? So it would seem that we would need to impose some kind of boundary condition on our flow for it to be well defined. And what kind of boundary condition? This is going to be related to interactions. So that's coming up. And in particular, you will see that only part of this boundary, we only need to impose boundary conditions on part of this boundary, and the part which corresponds to the coincidence set, where basically the configurations where both particles are at the same location in space at the same time, that's where we would need to put a boundary condition. So now here's an example of a space-like configuration. If photon is over there and electron is over there, you look at the past light cones of this thing, right? And if neither one of them is included in the past of the other one, this is a space-like configuration. A time-like configuration would correspond to this, where one of them is in the past of the other one, right? So we will only look at configurations of the first kind, right? Those are the space-like configurations. And if you think about that, you will see what the boundary of this space would look like. It would consist of light-like configurations, and one of the particles is on the past light cone of the other one. So those configurations provide the boundary of this space. Okay, what are the equations for a two-body that a two-body wave function needs to satisfy? So let's do it for one space dimension, because this is the one that we have completed so far. In one space dimension, the photon wave equation would be a 2x2 matrix, and because the diagonal blocks have to be traced 0, this means that the diagonal blocks are 0. So because they are just scalars now. So you're only left with two components. So you can think of it as you have two non-zero components, and then the wave function for the electron in one space dimension also only has two components. So if you want to look at the two-body wave function, you would have to take the tensor space over these things. So that would be 4 components, right? Belonging to this tensor space, and we're going to indicate these 4 components with the indices pluses and minuses for psi. So this is now our two-body wave function. It has 4 components. And each one is a function of all of the variables. That's important, because we are not just looking at a pure product states. We are looking at the general state. So this will not necessarily be a product. Okay, so how do we write equations? The usual way, you look at one-body operators. So starting with the Dirac operator for one body, you look at the tensor product with the identity, right? In one Dirac operator in one set of variables times the identity in the other set of variables, and then you will see that your wave function in the free case has to satisfy this system of equations. And if you are wondering what happened to that projection operator in 2 space dimensions, because the diagonals are 0, that drops out, so you don't see it. So now you see the wave function satisfies this system of equations, where in the photonic variables it is just a massless Dirac equation, and in the electronic variables is the massive Dirac equation. So this is the system of equations. Notice it is the same function that's satisfying these 2 equations. So you may worry that this will be too much to ask for the same function to satisfy two different PDEs, and indeed it would be worried, but however in this case there's nothing to worry about because these operators commute. But remember, this is the free case. That's why getting interactions in multi-time formalism is quite difficult. Because normally, how do you get interactions? You put in a potential in there to get interactions. If you try to put a potential in here, which depends on both variables, then that commutation relation is screwed up, and you can't find solutions to this thing. This becomes ill-posed. So that's why the usual way of getting interactions is not going to work with these equations. But fortunately, we already know that there were some boundary conditions which sort of the geometry of the problem dictated to us that there will be these boundary conditions. We do need to come up with boundary conditions. And as I already told you, these boundary conditions would involve putting conditions on where the two particles are at the same location at the same time. So, natural way to think about this is, well, if the particles are not going through each other, then we could set some kind of current equal to 0, going from one configuration to the next, or maybe think about in the Bohmian way, if we can set the relative Bohmian velocity of these particles equal to 0, then they're not going to go through each other, because when they get to each other, they slow down and come to a halt. So that would be one way of thinking of how to formulate a boundary condition for this problem. So one interesting thing that happens when you study the initial value problem for a multi-time wave function. So, and remember, this problem, despite appearances, this is not an ultra-hyperbolic problem. So in PDE literature, equations are divided into parabolic, elliptic, parabolic, hyperbolic, and then ultra-hyperbolic is when you have more than one time direction. And those equations are typically imposed, the initial value problem for them. However, this is not that situation. We have